I see a little silhouette of a man. Scaramouche, will you do the fandango? Thunderbolts and lightning, very, very frightening me. Galileo.
Hi, I'm Gustell, Preston.
And I'm Adison, Gregory.
And welcome to the world of Projectile Motion. A projectile is an object upon which the only force acting on it is gravity.
In Aristotle's theory of impetus, he thought that the object would move in a straight line until it was expended, at which point the object would fall straight to the ground due to gravity.
However, this theory was disproved by a young Galileo Galilei. Galileo Galilei was born in Pisa, Italy on February 15, 1564. He was the oldest of 7 children, and his father was a musician and a wool trader who wanted him to study medicine. However, Galileo wanted to become a monk. In the end, Galileo agreed that he would go to the University of Pisa and study medicine. At the time of his arrival to the University of Pisa, there was great debate over Aristotle's theory of projectile motion. According to legend, Galileo decided to try an experiment to disprove Aristotle. He needed to be able to drop objects from a great height. The perfect building was the Tower of Pisa, at 54 meters tall. Galileo climbed up to the top of the building, carrying a variety of balls of various size and weight, and dumped them off the top. They landed at the base of the building at the same time. This experiment disproved Aristotle's projectile motion. We will be throwing balls at various sizes and weights, as Galileo did, to show that their motion is in the shape of a parabola once you throw them. This is an example of projectile motion, and how Galileo disproved Aristotle's theory.
Football. Nice spiral! Soccer ball. Throw the next ball. Baseball. Throw it back, Logan.
Oh my god! In this representation, we will be showing how gravity works on objects in the same way, no matter the mass of the object. Please look.
Go.
In Aristotle's theory of motion, projectiles were pushed along by an external force which was transmitted through the air. His medieval successors internalized the force in the projectile itself and called it impetus. The impetus caused the object to move in a straight line until it was expanded, at which point the object fell straight to the ground. While objects projected through small distances may appear to behave in this manner, under close inspection and when viewing projectiles traveling greater distances, it becomes clear that projectiles do not behave in this manner. Using an inclined plane, Galileo had performed experiments on uniformly accelerated motion, and he now used the same apparatus to study the projectile motion. He placed an inclined plane on a table and provided it with a curved piece at the bottom, which deflected an inked bronze ball into a horizontal direction. The ball thus accelerated, rolled over the tabletop with uniform motion, then fell off the edge of the table. Where it hit the floor, it left a small mark. The mark allowed the horizontal and vertical distances traveled by the ball to be measured.
Activities included markers, check. Green ball, check. White out, check. Measuring tape, check. Poster board, aka RAM, check. Table, check, check, check.
Gregory.
Yay!
Our final results for the project ended up as so. After measuring the horizontal distance up the ramp and calculating the time it took for the ball to land on the floor, we came up with the mathematical result that t times squared is directly proportional to distance, y in centimeters. After coming up with a mathematical model, we graphed it and came up with this linear function. Parabolic motion, which is the graph that you are supposed to get for t squared equals directly proportional to y in centimeters.
So when we took our results, we got the following. When dropped from 0 centimeters on the ramp, it took 0.3 seconds for it to hit the ground. From 8, it took 0.4 seconds for it to hit the ground. From 16, it took 0.5 seconds for it to hit the ground. From 24, it took 0.6 seconds to hit the ground. From 32, it took 0.69 seconds to hit the ground. From 40, it took 0.72 seconds to hit the ground. From 48, it took 0.8 seconds to hit the ground. From 56, it took 0.9 seconds to hit the ground. From 64, it took 1 second. And from 72, it took 1.1 seconds to hit the ground.
And as you can tell, our data is quite close because we only measured 8 centimeters apart. Also, after linearizing our data and graphing, we came up with this mathematical model. Y squared equals
Centimeters squared over second over second. And then times x, which would be the For our procedure, we put a ball on an inclined plane on a table, and we made different measurement marks on the ramp that started from 0 to 72. And 72 was our height, and it was in centimeters, so it was increments of 8. And we had 10 of them, so the data is more accurate that way. So we would roll the ball and calculate the time that it took for it to hit the floor right here. And we learned that it took more time starting at 72 than at 0 because it was parabolic motion. When the ball fell, it would go like that.
The independent variable was the varying spaces or increments in which we started the ball and dropped it. The dependent variable ended up being the time it took for the ball to hit the floor. Our controls included the angle of the ramp and the position of the chairs